Good afternoon, and welcome to Hand-Wavy Chemistry. When wargamers and model train enthusiasts are building scenery and terrain, they start by adhering their basing materials using a simple white glue. Then, when that is fully dried, they come through and apply a layer of dilute glue to seal it and lock everything in place. However, before they add this dilute glue solution, they will often spritz the surface with some propan-2-ol, preferred IUPAC name. And when Klesh is doing his pay dirt reviews, he always adds some jet dry to the water before he begins panning for gold. The reason in both cases is because we want to ensure that the water penetrates into the material. And strangely enough, water on its own is not the best wetting agent. In order to explain why, we first need to understand intermolecular forces. Molecules are not innocent of their surroundings. They feel attractive and repulsive forces from the other compounds nearby. The weakest of these forces are known as London dispersion forces, sometimes also called temporary dipole interactions. Imagine you have an atom. In this case, let's consider a helium atom. It has two electrons orbiting around two protons and two neutrons. Now let's imagine we can freeze time and look. At some particular points in time, we will find that both of those electrons are on the same side of the atom. When this occurs, that side will be partially negative, and the other side will be partially positive. Other nearby atoms, while their electrons will see this imbalance in charge and be attracted to the positive end of our atom. These are London dispersion forces. They are the weakest type of intermolecular force, and they briefly pop up and go away. Because these forces involve the movement of electrons, atoms and molecules that have more electrons will experience more of these forces. This is why, as we go from methane to propane to hexane to octane and so on, we transition from gases to liquids to waxes to solids. Something else that influences the strength of these interactions is the geometry of the molecules. They need to get as close together and lined up in order to maximize the interaction. So if we think about fats, you can have saturated fats and unsaturated fats. Unsaturated fats contain double bonds. It is a permanent kink in the fatty chain. And if we think about cooking oils, they are made from polyunsaturated fats and are liquid at room temperature. Meanwhile, saturated fats, like animal fats, they are a solid at room temperature. This is because the long chains in saturated fats are flexible and can move around and line up as best as possible. But the double bonds that I mentioned in unsaturated fats, the permanent kink that they introduce prevents an optimal arrangement of those molecules, weakening their intermolecular interactions and lowering their melting point. The next strongest intermolecular force involves molecules with permanent dipoles. Now, we're not relying on the random movement of electrons to generate a charge imbalance. These molecules already have one built in. Having an electronegative element in an asymmetrical molecule means that our electrons are pulled towards that atom, and we get a permanent charge imbalance, a dipole. From this point, our molecules will once again want to arrange themselves and line up as best as they can to maximize that interaction. Because that dipole is always there, the strength of this interaction is higher than that of a temporary dipole. After our permanent dipole interactions, we move up to hydrogen bonds. Hydrogen bonds occur when we have a hydrogen atom bound to either a nitrogen, oxygen, or fluorine atom. These highly electronegative atoms pull the electron density away from the hydrogen. It is left with a partial positive charge. We have a permanent dipole. Furthermore, the lone pairs on nitrogen, oxygen, and fluorine are very dense. They create regions of electron density. So our hydrogen atoms, with their partial positive charge, they're going to see this electron density and be attracted to it, creating the hydrogen bond. And it is these hydrogen bonds that are responsible for water having such unusual properties. Methane has the same molecular mass as water, but it's a gas at room temperature, whereas water is liquid. Acetone, which is a polar molecule and has a molar mass about 3 times that of water, boils at 56 degrees Celsius, whereas water boils at 100 degrees Celsius, all thanks to hydrogen bonding. So why is it then that our scenery and terrain builders are spritzing their work with propan-2-ol and Klesch is adding jet dry to his water? Well, that comes down to the way that materials mix. Whenever we are going to mix two liquids, we have to consider what type of interactions are being given up and what type of interactions are being gained. If there is too much of a disparity between what a molecule is being asked to give up and what it's going to gain, then it's going to be reluctant to mix. We will find that they are immiscible. Oil and water, for example. In our water molecule, we will have temporary dipole forces, because all molecules have those. We will have permanent dipole interactions, and we'll have hydrogen bonding. Meanwhile, in our oil, we're only going to have those temporary dipole interactions. So the water would have to give up on those stronger positive interactions if it were to go into the oil. Because that's not thermodynamically favorable, instead we find that they are immiscible. But if we take water and a short chain alcohol, well, alcohol does have polarity to it, and it does have hydrogen bonding available. Now, those interactions might not be quite as strong as we might have in pure water, but they're going to be close enough that once we factor in entropy, they're going to mix, and we're going to have just one homogeneous solution. So, spritzing the terrain. The propan-2-ol, with its weaker permanent dipole interactions, will penetrate into the surface, seeding it with areas that can hydrogen bond. Now, when we apply our dilute glue solution, the water will see those hydrogen bonding locations and penetrate quicker and deeper, ensuring that we don't just put a layer of glue over the top, but rather down through the basing material, firmly holding it in place. Klesch, with his jet dry, he wants to change the surface tension of the water, weaken the water-water interactions. Those interactions and the surface tension they create can cause things to float. I have a short video where I demonstrate floating a coin on the surface of water. And for him, the worst thing that could happen would be that a piece of gold floated away and got lost. So he adds jet dry to weaken the interactions, break the surface tension, and ensure that all of the material goes into the water and gets wet so he can then pan it out. Another surfactant that I hope you use every day is soap, which helps water to remove dirt and grime from your skin. But that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is something you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.